Wednesday, or I might hit them up. We'll see kind of how far we get. Today we are going to be looking at what math calls relative extrema. And so I first want to start off by reviewing like what I hope you already know about relative extrema from previous math class. So in math, we have different types of extrema. And when I say that word extrema, that's just talking about minimums and maximums. That does have like some Greek suffixes on it. So when I say extrema, that's just the plural. Extremum will be a singular. But we're talking about relative and absolute extrema. We're going to learn about both of them, but because they have different definitions, we actually have to find them differently in calculus. So when I say absolute extrema, another word sometimes change for that is a global extrema. And absolute extrema is going to be the highest or the lowest point on the graph. So the highest or the lowest point on a graph. Whereas if I say a relative extrema, another phrase that we use instead of relative you sometimes see is local. And a relative extrema, instead of being the highest or the lowest, it's just kind of like a high point or a low point on the graph. So it's not necessarily the highest one or the lowest one. It's just going to be kind of like the highest of all the points around it or the lowest of all the points around kind of where we look at it. So here is just some random graph I made up. If I want to label different pieces of it, so this graph, I have arrows on the end of it, so it is always going down. So it does have this highest point here, which we call an absolute maximum, because it is the highest point on the graph. Also looking at this graph, we would say that there is no absolute minimum. Since this graph is always going down on both ends, it will never reach the lowest point. You can always keep going lower. But then all these other like high and low points would also be considered relative extrema. So for example, this point over here, it's not the highest point, but it is a high point, so it's a relative max. This point down here is not the lowest point, but it is a low point, so it's a relative min. And technically that absolute max, since it's also a highest point around it, it can also be classified as a relative max. I think, though, you know those words from Algebra 2, maybe. If not, now you do. But that's basically what we're going to be looking at this week. How can we use calculus to find the absolute extrema, and how can we use calculus to find the relative extrema? And I'm going to do the relative extrema first, because it tends to be most connected to what we just finished, and then we'll do absolute extrema towards the end of the week. Questions so far? All right. So one thing that we do have to be careful with in calculus is kind of being careful how like the language we use. So we already saw that we have to justify our answers for a lot of these. So we have to say like blah 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 is a relative max because. And one thing that can trip students up is just like the change in saying like is versus at, because that can actually mean very different things when you're writing out like a sentence to justify it. So I just want to make sure we're good with the words we use. So if I'm looking at this graph, I'm going to focus on that high point of -3.2 that is a relative maximum. It's a high point on the graph. So there's different ways we could state that that is a relative maximum. I can say something like the relative max is 2. So when I say like what is a relative maximum, I'm talking about the y value, like that's the highest point it reaches in that spot. I might say something like the relative maximum is at, and when I throw that at in there, then I'm talking about the x coordinate where it's occurring. So the relative maximum is at x equals 3. Or other ways you can say that that would be okay. You could say something like x equals -3 gives a relative max. The main thing I want to get there is just like the language, like if you're just talking about where something is, like I would not say, here's something that's wrong, the relative max is -3. That would be an incorrect statement because -3 is not the highest point on the graph. That's where the highest point is at, but that's not what the highest point is. So just be careful. Some people like being extra safe, and if they don't remember is versus at, they just give the coordinates. Like the relative maximum is at -3, 2, and that way you don't have to worry about when you use the x and when you use the y. I will say when we tend to talk about relative minimums and maximums, at least in this class, we're only going to be concerned more about where the x value of it is located at and not necessarily like how high or how low it is. So let's talk about how we find them. We have already discussed this unit, how we talk about intervals of increasing and decreasing. So here's that same graph, and this is going to kind of lead us into the conceptual part of it. We see that we do have like key points on the graph. So we're going to call those our critical points. We know that critical points occur when the derivative is equal to 0 or when the derivative is undefined. So if I'm looking at that graph, I can see that the derivative is equal to 0 at -3, 0, and 4. But then the derivative is also undefined at 2 because it's a corner or a cusp. And let's just talk about what the sign of the derivative would be. Since we already know how to do sign charts, those are familiar to us. To the left of -3, is that derivative positive or negative? The graph is increasing, so we know the derivative is positive. After -3, so between -3 and 0, what do we say the derivative is? Negative is decreasing, and then the derivative is positive, derivative is negative, and then the derivative stays negative. I'm going to circle those in different colors so they kind of stand out. And so I know we didn't make a full sign chart right now, but you can kind of see where we can use the sign chart to classify something as a minimum or a maximum. And I think it kind of makes sense. Like at -3, I knew that this was a relative maximum because the derivative went from positive to negative, which I think makes sense. In order for something to be a maximum, you first have to go up to it, and then you have to go down from it. So I would be able to see -3 right here. This is a relative maximum. How do I know? Because the f prime changes from positive to negative. And that's going to be kind of how we form our justifications. So instead of just saying like, hey, the derivative is positive here, or hey, the derivative is negative, we're going to be talking about how the sign changes in the derivative. I'm not going to write that for all of them, but we can kind of see it makes sense that 0 is a relative minimum. It's a relative minimum because the derivative goes from negative to positive. If you go down and then up, that's going to be a low point on the graph. Same thing for 2. That's going to be a relative maximum. Because if you go up and then down, you're going to have to be at a high point. And then we see that, yes, 4 is a critical point, but it goes from negative to negative, so it's not going to be an extrema because you're not going up to it or you're not really going down to it. So the idea behind finding extrema, if you were good with finding intervals of increase and decrease, it's literally the exact same steps except for your justification. So not going to be too much different today. I do want to kind of summarize it for you. So this is going to be, has a name. The name that we're going to call it is the first derivative test. And so the first derivative test can allow us to find extrema. The main idea when we're using this thing called the first derivative test is we're going to be looking at sign changes of your first derivative. So the steps I said are very similar to what you're doing when you're doing intervals of increasing and decreasing. Your first step is to find your critical points. The critical points occur again in 2 places, when the derivative is equal to 0 or when the first derivative is undefined. Similar to intervals of increasing and decreasing, after that you'll make a sign chart. And then make sure you always JYA, justify your answer. What does justifying your answer look like for this one? So again, if I'm talking about a maximum, you're going to have to go up first and then down to hit a maximum. So your justification will be something like, because f prime changes from positive to negative. You have to go up first before you can come down to reach a maximum. Similar, if something is a relative minimum, you have to come down and then up. So your reasoning will be because f prime changes from negative to positive.
So it's kind of like points of inflection, but for the first derivative, not the second?
Yes, it's like points of inflection, but with the first derivative. And you have to pay attention to the way it's changing. So positive to negative, up and then down, maximum. Negative to positive, down and then up would be a minimum. So normally, like most students are really okay with the first derivative test, especially once they kind of already mastered doing intervals of increasing and decreasing with the first derivative. So maybe a chance I know some of you are still writing that down, and then I'll switch. I just have one example, and then we'll talk about something called the second derivative test for Extrema. Anyone still writing that? All right. So here's the example I want you to do. Go ahead and do it without me. I think most of you can go ahead and start it. So I have the function, that's y is equal to x to the fourth minus 2x cubed plus 8. And I want you to identify the relative extrema using the first derivative test. So again, similar to intervals of increasing and decreasing, not even similar, exactly like intervals of increasing and decreasing. Find your critical points, make a sign chart, and then use that sign chart to justify your answers. And this one's a polynomial, so you only have to worry about when the derivative is equal to 0, because you won't have a case when the derivative is undefined. So I'm going to go ahead and work it out because I think this one's pretty short. So taking my derivative, I'm using the power rule. X to the fourth becomes 4x cubed. 2x cubed becomes 6x squared. I'm going to find when this is equal to 0. There's no denominator, so I don't need to worry about when it's undefined. Making sure I factor it. I factored out the GCF of 2 and x squared. So my critical points in order, I have 0 and 3/2. And then my factors I have are 2x squared and 2x minus 3. And again, I like putting vertical bars in the row of the factors of their critical points. And then we want to figure out when it's positive and negative. So 2x squared is the easy one, because what's going to be the sign of 2x squared? Always positive. We have 2 times something squared, always positive. And then we have 2x minus 3. So plug in something to the left of 3/2. 0 is a pretty easy one. We get a negative number. Anything bigger than 3/2 plugged in is going to give you a positive number. So what is this derivative overall. So this was a sign chart of y prime. I have a negative interval, and then a positive interval. So if I want to classify these as an extrema, is 0 going to be an extrema on this graph? No, like if you're thinking about what it looks like at 0, it's like the graph is decreasing, horizontal tangent, and then decreasing. So there is no extrema there. At 3/2, is that going to be an extrema on the graph? Yes. Is it going to be a minimum or a maximum? Minimum. So think we have a negative derivative and then a positive derivative. So it is going to be a relative minimum. Do have to justify your answer. So I'm going to say something like x equals 3/2 gives a relative minimum. How do I know it's a relative minimum? Because y prime changes from negative to positive. When you're justifying a relative extrema using the first derivative test, you have to talk about the sign change of y prime. So you couldn't say something like because y goes down and then up. Like you have to justify it using that derivative that you found. Questions on the first derivative test? All right, so first derivative test I think is pretty easy. Like you know how to make sign charts, you know how to take the first derivative and find when it's equal to 0 and undefined. We do have another way to classify extrema, and that's going to be something using the second derivative test. So the second derivative test, you might ask yourself like, well, why do I need a second derivative test if the first derivative test can give me intervals that increasing and decreasing? And my short answer that I would say to that now is, right now it's pretty easy for you to make a sign chart because of the functions that we're dealing with. Eventually, we'll be dealing with functions that are super, super complicated, where it can be next to impossible to make a sign chart with those types of graphs. So we want to have another method and a way to interpret the graph. And this is going to be something that is called the second derivative test. We know the second derivative does deal with the concavity, but we can actually use the concavity of the graph to help inform us about whether we have a relative minimum or a relative maximum. So I just took that same graph that I have here, and I just want to talk about just making sure we can identify like what the first derivative will be equal to, and then kind of approximate what the second derivative is equal to, and then we'll kind of go at the graph, kind of see how the second derivative test works from there. So like at x is equal to -3, again, it's just a made-up graph. Like I clearly see that that is a relative maximum. What is the first derivative equal to at -3 on that graph? I see I have a horizontal tangent, so I know the first derivative is equal to 0. Also at -3, is this graph concave down or concave up? Concave down. So it has that umbrella shape, so it's concave down. If it's concave down, I know the second derivative is less than 0, basically a negative value. This second one, I know I also have a relative minimum at x is equal to 0. Well, at 0, we have a horizontal tangent line. So we know that the first derivative is equal to 0. The graph makes more of a bowl shape there, so it's going to be concave up. So I know that my second derivative is greater than 0. Those are the two cases where we're going to be able to use the second derivative test. And so those are going to be the ones I'm going to focus on for the second part of these notes. And the idea behind it is, if you know you have a horizontal tangent in the graph, so like if you know you have a point and it has a horizontal tangent, when you also know the concavity of that graph, then you know whether that horizontal tangent is going to be the location of a minimum or a maximum. If that graph is bending downwards, then you're going to end up having a relative maximum. So if it's concave down, you have a relative maximum. If that graph is bending upwards, so if it's concave up, that point's going to be a relative minimum. So we can kind of use the bend of the graph and the horizontal tangent to talk about it. The cases where the second derivative test is not going to work is cases where the first derivative is undefined. Like if you don't have a horizontal tangent, it doesn't really matter which way it's bending. So like at x equals 2, we don't know what the first derivative is or the second derivative, it's undefined. And then at 4, yes, there is a horizontal tangent, but there's a flat part in the graph, and the second derivative is also equal to 0. Those last two cases, and we'll see why when I start showing examples, those are going to be cases where you're going to be forced to use the first derivative test. The second derivative test is not going to work for those cases. And again, I know many of you are asking like, well, again, if I'm good with a sign chart, can I use it? And the answer is yes, but we are going to quickly start encountering problems that we can't easily make a sign chart with. Like maybe you can't factor it nicely, or we'll see that there's like a mixture of variables in the problem. So we just want to have another method to classify extrema. So in the second derivative test, to give you like the main idea and the processes for it, some students mess up and think the second derivative informs us of the concavity. The second derivative test, just like the first derivative test, is another test for extrema. So we're going to call it the second derivative test. Main idea is we are looking at the concavity at horizontal tangent lines. Steps are very different. So one nice thing about the second derivative test, if you don't like making sign charts, or maybe you suck at making sign charts, you don't need to make a sign chart for the second derivative test. The first step to the second derivative test is you need to find when the first derivative is equal to 0. Notice I did not put critical points there because the second derivative test will not work when the first derivative is undefined. So you only need to worry about when the first derivative is equal to 0. Second step, you're going to need to find the second derivative, hence its name, it's called the second derivative test. And then third step, no sign chart, but you're going to plug the x values from step 1 into your second derivative. And then, of course, justify your answer, which I'll add for a step just to remind ourselves to always do it. JYA, justify your answer. And how do we justify our answer when we're using the second derivative test? You have to state two things always. If you only state one of them, then you haven't fully justified it. Think about a relative maximum. If you have a graph with a relative maximum, you have to clearly state that there's a horizontal tangent there, and then you also have to clearly state that it is concave down. So I'm going to say f prime of whatever that value is equal to 0, and f double prime of a has to be negative. And again, I just think about that visually. If you have a horizontal tangent line and your graph bends down, then that point where it's bending at is going to end up being a maximum. Likewise, if that graph has a horizontal tangent, but the graph is bending upwards, then your justification will be, hey, the first derivative is equal to 0, and the second derivative is greater than 0. If you're bending upwards, then it's going to be a relative minimum. So I'm going to look at just one example today, and that's where I'm going to stop at. Tuesday, you'll have time to start working on the homework. The notes I'm going to finish up on Wednesday will be the cases of like, what does it mean when the second derivative doesn't work? Which is not as important, because clearly if it doesn't work, you're not going to use it. But I wanted to kind of finish today's notes with just like, what does it mean and how do we use the second derivative? This is one topic that for whatever reason, students seem to just like forget it easily. Like, I guess because it's not like a sign chart, it's a little bit different. Don't forget it because it is super useful, especially when we start looking at graphs that are much more complicated. So here's the example I wanted to look at. Let's do a trig one. So again, second derivatives only work when you have a horizontal tangent. So go ahead and find the location of a horizontal tangent in this graph. So again, horizontal tangents are going to be when the derivative is equal to 0. And feel free to pause there, and then we can kind of finish out the problem together. But first step, what you should be able to do, find when the derivative is equal to 0. And make sure you pay attention to the interval that we're looking at. So some good review of trig equations, which is what we're doing in my pre-calc class right now. The derivative of tangent is secant squared, the derivative of 4x is 4, and then that plus 4 just goes away. Horizontal tangents occur when the derivative is equal to 0, so I have secant squared of x minus 4 is equal to 0. Add 4 to both sides, making sure we can take the square root, we have to include the plus or minus. I don't like thinking in terms of secant, but we know that secant is the reciprocal of cosine. So saying secant is equal to plus or minus 2 is the same thing as saying cosine of x is equal to plus or minus 1/2. That helps you think about it. So we wanted to figure out when cosine is equal to plus or minus 1/2 along the interval from negative pi over 2 to pi over 2. Thinking about your unit circle, that's basically the right half of the unit circle. Well, cosine is equal to only positive on that side, so I guess if you left off the plus or minus, you wouldn't miss any answers. But we do have one answer when x is equal to pi over 3. That's the one up here. The other answer is the one in the fourth quadrant, which on the unit circle would be 5 pi over 3, but that's not within the interval from negative pi over 2 to pi over 2. What answer is within that interval? Negative pi over 3. So those are the two values that we get of where we have horizontal tangents on this particular graph within that interval. Questions on how I found those x values? All right. So then it tells us that we're using the second derivative test to justify my answer. So if this was the first derivative test, I would make a sign chart, create my sign chart, figure out when it's positive and when it's negative. The second derivative test states, I just need to know, well, I have these two horizontal tangents. I want to know if the graph is bending upwards at those horizontal tangents or bending down at those horizontal tangents. So I want to go ahead and find the second derivative. Good review of the chain rule here. That is secant squared, so we need to use the chain rule. So 2 comes down in front. Secant would now be raised to the first power. Then we have the chain rule. The derivative of secant is secant of x times the tangent of x. That minus 4 is just going to go to 0. Definitely we can simplify it to make the math a little bit easier. And I get y double prime is equal to 2 secant squared of x times the tangent of x. So here's like the big idea with the second derivative. I have these two x values that I want to figure out what's happening at them. I have the x value of negative pi over 3. I also have this x value of positive pi over 3. And I want to plug those values into my second derivative. We can cheat a little bit. That's a little bit hard to see. I don't care like what the actual number is. I just need to know, is this going to be positive or negative? So plugging in negative pi over 3, I have 2, the secant of negative pi over 3 squared, and then the tangent of negative pi over 3. Let's think about what this second derivative is going to be. 2 is a coefficient. Is it positive or negative? It's positive. And then I have secant squared. Who cares what the secant of negative pi over 3 is? Because when I square it, it's going to be what? Positive. And then I have the tangent of negative pi over 3. Well, negative pi over 3 was in quadrant 4. Tangent in quadrant 4 is positive or negative? Negative. So tangent is negative. So I see that the second derivative is less than 0. So then let's do the same thing for pi over 3. Let's go ahead and plug in pi over 3 into the second derivative. So I have 2 times the secant of pi over 3 squared times the tangent of pi over 3. Again, you can't evaluate it, but we just care about the sign of it. 2 is positive, anything squared is positive. Pi over 3 is in the first quadrant. Tangent in the first quadrant is positive. So this second derivative is greater than 0. That's enough information to figure out whether we have a relative minimum or a relative maximum. Let's talk about x equals negative pi over 3 first. So I know there's a horizontal tangent there. So like, here's my horizontal tangent. When I plugged in negative pi over 3, I saw that my second derivative was less than 0. So is my function concave down or concave up? Concave down. So I'm going to draw it concave down. So at negative pi over 3, is that going to be a relative minimum or a relative maximum? We know it's a maximum. Same thing for the other one. At pi over 3, that's a horizontal tangent line. That horizontal tangent line, the second derivative is positive. Is it concave up or concave down? Concave up. So if it's bending upwards, that's going to be a relative minimum. So how do we justify our answers? And then I'll answer questions that you may have. You have to clearly state both conditions being satisfied. So my justification, I'm just going to kind of write it off to the side. I have x equals negative pi over 3 gives a relative maximum because y prime of negative 3 pi over 3 is equal to 0, and y double prime of negative pi over 3 is less than 0. And yes, you have to state all of that. You have to state clearly that there's a horizontal tangent there, and the second derivative is less than 0. And then for the other one, x equals pi over 3 gives a relative minimum for a similar reason, because y prime of pi over 3 is equal to 0, and the second derivative is greater than 0. Fun stuff, right?
Yes.
So I'm going to stop my notes there today. I don't think your brains could handle much more. But tomorrow, or not tomorrow, tomorrow you can start working on your homework. The rest of the notes we're basically going to talk about, like, well, what happens when the second derivative is also 0? Like, what happens when the first derivative is undefined? Like, what does that mean in terms of the concept of the second derivative test, which again is a concept that will show up several times this semester, several times next semester. To give you a checklist, because I don't want you to feel overwhelmed with what you have to get done. So your homework for tonight honestly shouldn't take you too long, hopefully, to do. So homework number 4, it's 2 pages. I pasted it into one note so you'll see it. But on that first page, it's just numbers 20, 24, 28, 42, 46, and 47. That first set's going to be the first derivative test. And then the page 192 with numbers 36, 38, and 40, that's going to be the second derivative test. So tomorrow is a teacher workday. Wednesday we'll finish up these notes. The quiz I'm passing out Friday will be a take-home one, so you'll be able to do it at home. It won't be due until the following Tuesday. During the teacher workday tomorrow, in case you do have some things that you want to get done, like clearly homework is the priority for most students. I am going to pass out the quiz 4A to you. If you did take it last week, you can on that if you want to go ahead and start getting ahead. The key is posted in the answer keys folder in Teams. Or if you missed the quiz, / if you want to do recovery on a test you didn't do too well on, whenever you're free tomorrow between regular school hours, send me an email and I will send it out to you to take at home virtually. So that's for people who either you're out on Wednesday and you need to make up the quiz 4A. It's a completely different one from everyone else's, but same topics. Or if you didn't do well on tests and want to do recovery, I'm not going to put a set time on it, but like if you email me at 5, like I'm not checking email after 5. Probably just be anxious about election results at that point. But during the school day, feel free to email me and we can get that taken care of. Other than that, I'm going to go ahead and end today's notes. Those of you at home, if you want to go ahead and sign out, you can. If you have questions. And if you're at home, I already sent back to you your quiz through OneNote. And then if you're in class, you're about to get your quiz right now.